the last class PPTs to your class CRs. I think 5 or 6 people, the CRs, they gave the mail IDs to me. I hope everyone received the PPTs, presentations to your mails. Okay, go through the presentations so that you will get the clarity. Now, after completion of each and every class, I will share on the day presentation to your class CRs on the same day itself, so that it will be very clear to you people. Okay. Today we are going to start the new topics, that is the breakdown mechanism, and there are different breakdown diodes are there. Among those 3 diodes, we are going to start today the tunnel diode. We are going to see the tunnel diode. Okay, first we will see what is the breakdown mechanism. Now why it is occur in our PN junction diode. Now what is that mechanism? What are the different types of breakdown mechanisms that we are going to discuss today. Okay, just I'm recalling the PN junction diode VI characteristics. Okay, now this is the VI characteristics of PN junction diode. Now already you people aware of this VI characteristics of PN junction diode. Now just 1 minute. Okay. This is the VI characteristics of PN junction diode. Now this is the curve in the forward bias direction, and this is with respect to your reverse bias. Now we are going to operate the PN junction diode for the forward bias. Now what is the basic characteristics of PN junction diode in forward bias? Now up to the threshold voltage, there is no current flow through the PN junction diode. Now whenever the applied voltage is greater than the threshold voltage, the threshold voltage is nothing but it is the 0.7 volts for the silicon diode and 0.3 volts for your germanium diode. If it is more than the threshold voltage or cut-in voltage, then the current will start increasing in case of your forward bias. That's why in the forward bias, maximum amount of current flow through the PN junction diode. Now coming to the reverse bias. Now in reverse bias, generally there is zero current. There is no current flow in the reverse bias in case of PN junction diode. Even though when you are applying the reverse voltages, that means if you are configured your PN junction diode in the reverse bias configuration, there is a negligible, a small amount of leakage current is going to flow. This is a small amount of leakage current that is going to be there in reverse saturation current. That theoretically we may call it is zero current in the reverse bias case. Now see, now for the same simple PN junction in the reverse bias case, if you apply the -3 volts, I'm applying -3 is nothing but reverse voltage. And now there is no current flow through the diode. Only minority due to the minority charge carriers, only the reverse saturation current will flow in reverse bias. Now I increase my reverse saturation current to -5 volts. Now still there is a same leakage current is going to be flown. But still, if you are increasing more and more reverse voltage, at some point of time, there is a breakdown mechanism will occur. Breakdown in the sense, suddenly, huge amount of current is flowing through the device that causes the damage of the device. That's why, practically, in the PN junction diode, we will not operate our basic PN junction diode in the reverse bias for the higher reverse voltages. Now, up to the some amount of reverse voltage we will apply, and we can observe the PN junction characteristics. Still, if you are applying the more and more reverse voltage, then the breakdown will. Breakdown is nothing but there is a sudden change in the current, sudden increase in the current that causes the device to damage. Now, in case of PN junction, from the basic construction of PN junction, the doping concentration is very, very less. At the same time, it cannot tolerate this much amount of current. Now, that's why it may lead to the damage of current. Now, what is the main reason for the breakdown mechanism? This is applying the higher amount of your reverse voltages that causes the breakdown. That means if suddenly if your vehicle or something breakdown means it was stopped some due to something. But in this case of your device, the breakdown occurs means a sudden change of current. Up to this point, only minority charge carriers, very microamperes of current is small amount of leakage current is flowing. But at this point onwards, huge amount of current starts flowing through the diode. Now this causes the damage of the diode. Now, what are the different types of breakdown mechanisms we are having that we are going to see today's class? Right. Now there are three types of breakdown mechanisms in the semiconductor devices. The first type of breakdown is we are calling as our avalanche breakdown, and second type of breakdown is Jenner breakdown, and third one is thermal breakdown. Generally, you people are going to see only these two types of breakdowns. That is a Jenner breakdown as well as your avalanche breakdown. Now, these two breakdowns, the conceptual point of view, almost they are looking like the same. But the thing is, now what is causing the Jenner breakdown and what is causing the avalanche breakdown? There is having a small demarcation line. If you are able to understand that small demarcation line, then these two breakdown mechanisms will be very clear to you people. Okay. First, we will see the avalanche breakdown. First, I will explain you with the help of the points wise. Then I will show you the pictures, diagrams. Then you will get the clarity. Now, when there is no bias applied to the diode, now just imagine the situation. Now, if I'm not applying any bias to the diode, now in this case, there are certain number of thermally generated carriers are there. Because already I told you, at the room temperature, some of the carriers will be available. Those are generated by the due to the thermal generation. Now, when bias is applied, these electrons and holes acquire sufficient energy from the applied potential to produce the new carriers that may be going to be from the valence electrons from there to the conduction band. Now, this is a phenomenon of the forward bias as well as your reverse bias phenomenon. And these thermally generated carriers acquire additional energy from the applied bias. Now, if they strike the lattice and impart some energy to the valence electron, so the valence electrons will break away from their parent atom and they become the free carriers. Okay, this I will explain with the help of the diagram. Now, these newly generated additional carriers acquire more energy from the potential since the bias is applied. Now, so they again strike the lattice and create more number of free electrons and holes. This process goes on as long as bias is increased and the number of free carriers get the multiplied. This phenomenon we are calling as the avalanche multiplication. Okay, I think with this points, you people are not getting the clear. Then I will show you this with the help of some picture. Now, what is avalanche breakdown? Right. See, in a forward bias PN junction, now what is going to happen? The current will flow from P to N. The forward bias case. Just I'm recollecting. Just in the PN junction, that means electrons are majority charge carriers. Forward bias from the N to P, they are moving electrons. Current is from P to N. This is for the forward bias junction. Next, if it is a reverse bias junction, the current flow is due to N to P. That is due to the minority charge carriers. Now the minority charge carriers, they are moving from this to this. That's why reverse saturation current is flowing from N to P. In the forward bias, that is P to N, the majority current is flowing. In the reverse bias junction, the minority current is flowing from N to P. Now see, what is an avalanche breakdown? Now see here. Now this is the depletion region. Now what is present in this depletion region? Now in this depletion region, now we are having immobile ions are there. These are nothing but our immobile ions. Now when we combine P-type and N-type material, immediately there is a recombination is takes place here. Now that means in this there is no charge carriers. It is becoming as depleted carriers. Carriers are depleted here. They are leaving the immobile ions. Due to that, some electric field is going to be developed that we are calling as your barrier potential. Generally, the barrier potential we are calling as a 0.7 for your silicon and 0.3 for the germanium. Now, in the depletion region, only immovable ions are there. Okay. Now, some electric field is also already it is occurred due to the inbuilt potential, due to the barrier potential. Now, what is an avalanche multiplication? Now, when you are applying the more and more reverse bias voltage, now what is the reverse bias voltage? I am taking the minus 5 volts, or it is still I am increasing minus 7 volts, or in minus 8 volts. That means for the more and more reverse bias voltages, now what is going to happen? Now there are some free electrons. Now this side some minority charge carriers electrons or majority charge carriers are this side. These free electrons, what they will do? Now they will collide with the lattice structure. Now see the silicon lattice structure, already 4 electrons are, they are bounded with the other lattice. That means this is one electron hole pair, this is one covalent bond, and this is one covalent bond. That means the silicon atom, 4 free electrons are, they form the 4 covalent bonds. Now, due to the excess reverse voltage, applying the more and more reverse voltage, this free electron that is colliding with the silicon lattice structure, so that now whenever it is colliding with this one, what is going to happen? Now this electron is going to release here. It is becoming the free. Now see here. Now whenever this electron is colliding to this covalent bond will break, and this electron will comes. It is becoming as the free carrier. Now see where it is happening. Now this is happening in case of your depletion region. In the depletion region, immobile ions are there. That means these are perfectly bounded. There is no free electrons and the free holes in case of depletion region. But whenever due to the external more and more reverse voltage, whenever minority charge carriers, now they are hitting the lattice, they are hitting these atoms in the depletion region. Now so that this is hitting this lattice structure, so that it is generating one more electron. Now what will happen? One electron came to this silicon atom, it hit the one valence electron. Now this another electron is going to be released, thereby creating one hole here. Now this 1 plus 1 now is becoming the 2 free carriers here. Now what will happen? Now see avalanche break. First initially one electron came to here and it is hit your atom. Now one of the valence electron, now it is going to break the bonds and it is becoming the 2 electrons are, it is becoming 1 is becoming 2. Now these two, they are colliding with the 2 more atoms. Now how many they are releasing? They are releasing 2 more free electrons. Now this 2 and 2, this becoming as a 4. Now these 4 once again they are colliding with the 4 more silicon atoms present in the depletion region. Now they are releasing the 8. That means they are multiplied. The free charge, the charge carriers in the depletion region, they are going to be multiplied. Due to this multiplication of charge carriers, huge amount of current will flow. That current we are calling as your reverse saturation current. That is huge amount of current will flow. So immediately the breakdown will occur. Breakdown in the sense, in the reverse bias, up to some amount of time, there is no current flow in the reverse bias. But whenever these are multiplying, due to this free charge carriers, the current is going to be multiplied. Current is doubled and they are going to multiply. There is sudden increase in the current. This sudden increase in the current will cause the device to damage. Now, if any breakdown will occur due to this process, that means if any free electron is colliding with the atom and that is releasing the one more electron, and these two they are colliding with the another 2 atoms, they are colliding, they are releasing the 4 free electrons. Now like this process will continues, and the breakdown occur due to this process we are calling as the avalanche breakdown. I hope this will be clear. Now this is what I said in this slides. Now see once again I will show you this one. Now what is avalanche breakdown? Now when they strike the lattice, what will happen when they strike the lattice? When they strike the lattice and impart some energy to the valence electrons. Now generally these in the avalanche breakdown, valency, those are loosely coupled valence electrons only, they are going to break the bonds. Now in case of Jenner breakdown, due to the external huge amount of electric field, the electric covalent bonds are going to rupture. But in avalanche breakdown, these covalent bonds are not rupturing. But what is happening? The valence electrons, which are loosely bounded, now those electrons only they are uh, getting some energy and they are moving away from the basic atom. Now, what is happening? It is getting some energy to the valence electron. So the valence electron will break away from their parent atom and become the free carrier. These newly generated additional carriers, they will acquire more energy and they will form the potential. Since the bias is applied, reverse bias, more and more heavy reverse bias is applied. So they again strike the lattice and create more number of free electrons and holes. This process goes on as long as bias is increasing. As long as your reverse voltage is increasing, this process will continue and the number of free carriers is getting the multiplied. Now this is very, very important thing. And now this is known as the avalanche multiplication. And the breakdown due to this process we are calling as avalanche breakdown. Since the number of carriers is large, the current flowing to the diode, which is proportional to free carriers, also increase. And when this current is very large, the avalanche breakdown will occur. I hope this avalanche breakdown is clear. Okay. Now, what is JNTUH breakdown? In the JNTUH breakdown, now what we are doing, before going to the JNTUH breakdown, first we will see what is a JNTUH diode. Now, what is the construction of JNTUH diode? Now, we are not going to see in detail because JNTUH diode is not there in your syllabus. Now, I will explain you a simple, the basic concept, 1 to 2 minutes. Then I will come back to this slide. Right. Now, this is the JNTUH diode. Now, I will show you the construction of the JNTUH diode. This is the basic structure of your JNTUH diode. Now, JNTUH diode is the one type of PN junction diode that is not a separate diode. But the problem with the PN junction diode is in the reverse bias. Now, what is the practical switch? If we want to use the PN junction diode as a switch, if I am turning on the switch, 100% current has to flow. If I am turning off the switch, 0 current has to flow. But if I use the PN junction diode in the reverse bias condition, that means if I am turning off the switch, but still there is a leakage current, still some current is flowing. Now that's why that is not a practical switch. We cannot use PN junction diode as a perfect switch. Now how to utilize the reverse condition in the reverse bias operating? We can use the reverse bias by changing the structure, not the structure, by changing some parameters, so that in the reverse bias also we can perfectly utilize the PN junction diode. That type of diodes are nothing but your JNTUH diode. JNTUH diode is going to operate only in reverse bias. In the forward bias, it is looking like a normal PN junction diode, but in the reverse bias, it is acting as a voltage. That means voltage regulator. Now, even though how much voltage we are getting, it is produced with the constant. That means now whatever the stabilizers we are seeing in the nowadays, there we are going to use the JNTUH diodes. The JNTUH diode is nothing but a constant voltage regulator. That we will see here. Now the difference between the PN diode and the JNTUH diode is, now you people are able to see a P plus and N plus. Now what is this P plus and N plus? In case of PN junction diode, it is only P and it is a N. Now already told you P is an extrinsic semiconductor, N is also extrinsic semiconductor. What is P-type material? Doping with the trivalent impurity is P-type material. Doping with pentavalent impurities is nothing but your N-type material. Now what is the P plus? Now the difference between P and P plus is, now see, I'm giving one more thing. In the intrinsic semiconductor, how many electrons and holes are there? 50%. In the P-type semiconductor, majority charge carriers are holes. That means holes are greater than. Now what is P plus is heavily doped semiconductor. For example, in the P region, I'm using 1 atom for 10 power 3. That means if I used one dopant, one trivalent impurity for 10 power 3 atoms, 1 atom for 10 power 3. Now P plus is, it is heavily doped. That is 1 for the 10 only. That means, for example, in the P material, I am using the 100 trivalent impurities. In the P plus, I am using 1000 impurities. That means the difference between P and P plus is P is it is an P-type material doped with trivalent impurities. P plus is heavily doped. Now, heavily doped in the sense, a huge number of holes will be available in the P plus region. Huge number of electrons are available in N plus region. Now, see, this concept is very, very important for the tunnel diode also. If I are using the doping concentration, now what we have done, we are increasing the doping concentration. If we are increasing the doping concentration, what is the first result is immediately the width of the depletion region will decreases. Now normally in the reverse bias, what is going to happen? The width of the depletion region will increase. But if you change the doping concentration, due to that huge amount of charge at both the sides, because heavily doped regions are there, due to this, the width of the depletion region will reduces. Now remember this point. This point is very, very important. The width of the depletion region directly proportional to your doping concentration. If you are doping more and more heavily doped is there, ultimately the width of the depletion region is very, very narrow. Now, in case of tunnel diode, now in the GNR diode, the 1 part for 10 power 3 I am taking. For the tunnel diode, 1 part for 10 power 8. That means a huge amount of doping will be there in case of tunnel diode. Now, tunnel diode, almost very small, thin depletion region will be there for tunnel diode. Now, why I am telling the tunnel diode here is only the one point you are going to remember. What is the thing? If you are increasing the doping concentration in the P region and N region, because of this heavy doping, the width of the depletion region will decreases. Just remember this point only. Now, what is the CEDA? Whenever due to this excess thing, that means even though externally you are applying the reverse voltage, N is connected to positive terminal, P is connected to negative. This is a reverse bias voltage you are applying. GNR diode is always connected in reverse bias only. We are going to use in reverse bias. Now, due to this more and more reverse voltages, what is going to happen? All this width of the depletion region is very small because due to the heavy doping. Now, there is an electric field is greater than 300 kilovolts per centimeter. Now, see the electric how much electric field is going to be developed within the depletion region. Here, more amount of electric field is going to be developed. This due to the heavy doping. Now, what is going to happen? This is see the Jenner effect. What is the Jenner effect? Now, the difference between avalanche effect and Jenner effect is in the avalanche breakdown, the breakdown is not due to the electric field, but in the Jenner breakdown, that breaking of bonds that is due to the stronger electric field. Now, what is going to do? Due to the strong electric field in the Jenner diode, now they will rupture the bonds. Previously, the loosely that means loosely valence electrons only they came out from the covalent bonds. But in this case, due to this high electric field, now some of these bonds are going to be broken and they will be come out from the lattice structure. Now this effect we are calling as a Jenner effect. Now see, now what is happening? If you are applying the high amount of electric field, that means already potential energy is developed, very huge amount of electric field is developed in the depletion region. Due to that, now see, this electron is this bond break, this bond was ruptured and one free electron came out. From this one electron came out, from this one free electron came out, and like this, for so many electrons at a time, they will break the bonds and they will comes out and they will become as a free carrier. Whenever this type of charge carriers, they will come more and more to the, they'll break the bonds and they are coming out as a free charge carrier. Due to this, there is a sudden increase of current. That due to that current we are calling as a breakdown mechanism. Now that current we are calling as the Jenner current. Now the Jenner effect is mainly due to the presence of stronger electric field. Now, what is avalanche breakdown? Avalanche breakdown is mainly due to high reverse voltages. This is due to high voltages, and now Jenner breakdown is due to stronger electric field. Now this is the difference between avalanche breakdown as well as your Ginner breakdown. Now see, this is for the normal case. Normal PN junction diode, the breakdown will occur at the breakdown voltage. For example, I am assuming at the minus 7 volts, the normal breakdown occurs for the PN junction diode. This for the normal case. But for the Ginner diode, now at this point only breakdown will occur, because already a strong electric field is developed in the depletion region. Due to that, now from this point only at the Ginner voltage onwards, it is constant amount of current is going to be flow. Huge amount of current is flowing irrespective of your voltage what you're applying. That's why now what is the meaning of this breakdown voltage is, if the breakdown voltage is less than 4 volts, now that effect we are calling as a Ginner effect. That means the reverse voltage is less than 4 volts. Now for this less than 4 volts only, if any breakdown will occur, that is due to the Ginner effect. The breakdown voltage is greater than 6 volts, that means more reverse voltage due to the more and more voltage, that is the avalanche effect. Between 4 and 6 volts, now both this breakdown, avalanche and Ginner, these breakdowns, you can observe these two types of breakdowns. But in the MCQs are generally, if 4, you are not going to see the 4, they are going to take the reference as 6. Now if it is less than 6 volt, that is a Ginner effect. Greater than 6 volt, we are calling as that as avalanche. I hope this is clear. The breakdown mechanism is clear. The main difference is, if due to the strong electric field, that means the rupture of covalent bonds. The covalent bonds will be ruptured and they are releasing the free electrons. Due to that electrons, charge carriers, if any current is flowing, now due to that current, if any breakdown will occur, that is a Ginner breakdown. Now, if due to the larger reverse voltages, if any breakdown will occur, that is due to your avalanche breakdown. Now, this is the difference between avalanche breakdown and Ginner breakdown. Now that once again we will see the statement here. Now what is the statement you see? Now what is the Ginner breakdown? If the electric field is very strong, now if the electric field is very strong, to disrupt or break the covalent bonds, there will be sudden increasing number of free carriers and hence large current and constitute breakdown we are calling as a Ginner breakdown. That is what I said just now. Due to the electric field, strong electric field, if any breakdown will occur, that is your Ginner breakdown. Even if thermally generated carriers do not have sufficient energy to break the covalent bonds. Remember, for example, at the room temperature, at the 26 degrees temperature, and now these electrons, they will, that means the free charge carriers, they will acquire some energy. So even though that energy is not sufficient to break the covalent bonds. Now, if you want to break the covalent bonds, what is required? Very strong electric field is required. Now that's why this is called as a Ginner breakdown. What is Ginner breakdown? Due to very strong electric field that disrupt or break the covalent bonds, that is sudden increase in the current. Now that due to your Ginner breakdown. This is about your Ginner breakdown. And now what is the value? Just see here. Ginner breakdown, you can see a junction having the narrow depletion layer. Now all I told you, if your doping concentration is very high, the depletion region is very narrow. That means the width is very less. Now there is a tunneling of charge carriers also will take place, and very high field intensity will be there. It will have the Ginner breakdown effect, approximately 10 power 6 volts per meter. This much amount of electric field will be there. If the doping concentration is high, now remember this is the very important thing for the next topic. If the doping concentration is high, now if you are doping the material with the highly, you are doping with the P type and N type, the depletion region is narrow and will have high field intensity, that will cause the Ginner breakdown. The Ginner diode, tunnel diode, they are looks like a little bit safe, but the concept is different. But the main thing is, this is Ginner diode is also heavily doped PN diode. Ginner is also heavily doped, but compared to Ginner, tunnel diode is more heavily doped. That's why if it is for Ginner diode only, depletion region is narrow. For tunnel diode, almost very thin depletion layer will be there. That is the difference between Ginner and the tunnel mechanism. Tunneling mechanism we will see the after this thermal breakdown. Okay, avalanche breakdown is clear. Next one is Ginnar breakdown is clear. What is the third type of breakdown we are having? Thermal breakdown. The name itself, it is saying thermal breakdown. Now, if your diode is biased in the bias voltage as well within the breakdown voltage at room temperature, there will be certain amount of current which is less than the breakdown current. Now, what we are doing? Keep the bias voltage as it is. That means the reverse voltage, I am have my bias voltage is I am keeping as a fixed minus 5 volts. Just imagine, I am assuming if you increase the temperature, now initially the 26 degrees temperature, now if you increase the temperature to 36 degrees, now what I told you, now for every 10-degree raise in temperature, the reverse saturation current will doubles. Okay, reverse saturation current is nothing but the current due to minority charge carriers. Now it is current is doubling means reverse the charge carriers are also they are doubled. That means now if you are fixing the bias voltage as it is, if the temperature is increased, that is due to the thermal energy, more number of carriers will be produced and finally breakdown will occur. This breakdown is thermal breakdown. If any breakdown, if the breakdown occurs due to the temperature increment, that is calling as thermal breakdown. If any breakdown occurs due to the strong electric field, that is a Ginnar breakdown. The breakdown occurs due to larger reverse voltages, that is nothing but your avalanche breakdown. That's it. This is with respect to your breakdown mechanism. Now we move on to our the first breakdown diode, that is the tunnel diode. Now this concept little bit not the typical. Now if you focus on this tunnel diode, then it will be very easy for you. Yes, my voice is clear to everyone. Is it clear my voice? Okay. Okay, right. Now we'll move on to the tunnel diode. Just to pay a little bit more attention with this tunnel diode. See, if you understand the concept, then you can write very easily with your own. That's why for that intention, I'm creating some of the animations also and all those things. Right. Tunnel diode. Now, other name of tunnel diode is nothing but your Esaki diode, ESAKI, because the scientist Leo Esaki, he has proposed in 1958. Now, with his name only, and now this name tunnel diode is naming as your Esaki diode. Other name of tunnel diode is Esaki diode. Now, what is this tunnel diode? Just see, this is very important slide. It is a heavily doped PN junction. Impurity concentration is 1 part in 10 power 3 as compared to 1 part in 10 power 8. Just imagine 10 power 8 is nothing but I think it is 10 millions or 1 billion, that is. For 1 billion atoms, if you are adding the one impurity part, that is nothing but your PN junction diode. But for every 1,000 atoms, for every 1,000, one part you are adding. That means almost impurity is nearly double. Now PN junction is very lightly it is doped, but in case of tunnel diode, it is very heavily doped. See here, it is tunnel diode 1 part in 10 power 3, PN junction 1 part in 10 power 8, for Ginnar diode 1 part in 10 power 6, that is in medium. That's why Ginnar diode is also heavily doped as compared to PN diode, but as compared to Ginnar diode, tunnel diode is more heavily doped. Now, width of the depletion region is very small in tunnel diode, 100 angstroms only, very thin layer. That means very thin layer that is separating the P type as well as the N type in the tunnel diode. Now, it is generally made up of germanium and gallium arsenide. Remember the material, but tunnel diodes, they are not going to made up of silicon. They are going to made up of either germanium material or gallium arsenide. This is a compound material. Now this is these two materials we are going to use for the tunnel diodes fabrication. Now it shows the tunneling phenomenon. The circuit symbol for this will be, now what is the circuit symbol for this? Tunnel diode symbol is, it has a reverse E. Now what is the PN junction diode? Now PN junction diode is, it has an anode and a vertical line here. This is a PN junction diode. Okay, now if it is the like this, that means it's the E shape, reversed E, that is nothing but your Isakina. Flipped E is nothing but your the symbol for tunnel diode. Remember, the diodes, the symbols are very, very important. If this is not there, this is a PN diode. Now, if due to this is nothing but a symbol for your tunnel diode. Okay. Now, you see, this is the complete concept is with only single slide. It is a single slide. Now, what is the barrier potential? Barrier potential is nothing but, now this is the depletion region is nothing but your, in the depletion region, generally for PN junction diode, there is an inbuilt barrier potential. The barrier potential is for silicon, that is 0.7 volts. Now, in case of tunnel diode, now what is the barrier potential that VB is given by, remember this expression, small e to your angstroms. Really, that is meter cube, that is given by VB by E into N. Now see, now what is this meaning? So the width of the junction barrier varies inversely as a square root of the impurity concentration. Now see, width of this junction barrier varies square root of inversely the square root of inversely proportional square root of. Now this is the width is nothing but your more. For that purpose only I kept this relationship. Now in tunnel diodes, by increasing the impurity concentration Na, W can be reduced to 5 micro to 0.01 micro angstrom. That is very, very, very small thin layer. It is separating the P region as well as N region. According to the classical mechanics, a particle must possess which is at least equal or greater than the barrier potential to move from one side to another side. Now, what is this meaning? Now, what is the classical mechanism? Classical mechanism. There is a P region is there, N region is there. That is for normal thing. There is a barrier potential, inbuilt potential 0.7 volts is there. Now, when the moment of charge carriers will take more than the barrier potential, if you apply the more than the 0.7 volts, then only diffusion of charge carriers will take place. That is the general mechanism. But when the barrier width is very, very thin, like the 0.01 microamperes, according to Schrodinger equation, there is much probability that an electron will penetrate when forward bias is applied to the diode. Now see the concept. If barrier potential, for the normal case, barrier potential is 0.7 volts, more than the 0.7 volts only, the forward bias, the current conduction will take place. But if the width of the depletion region is very, very small, very, very thin, even for a smaller forward bias voltage, 0.1 volt also, the current flow will take place. That current flow will take place due to the tunneling mechanism. That means the electrons will tunnel from the N region to the P region. Now, when the electron can penetrate, whenever the width of the depletion region is very, very thin. When the depletion region is very, very thin, that means impurity concentration is more. I hope this slide is clear. This is clear. Now the complete tunnel diode. A particle must possess the potential which is at least equal to or greater than the barrier potential. Then only they will move from one side to another side. That is for the classical mechanism. That is for PN junction diode mechanism. But if the width is very, very thin, very, very small, according to Schrodinger equation, what is happening? Even though it is not reaching to the barrier potential, less than that also, now there is a current. That current is due to the penetration of electrons from the one side to another side. That is due to penetration of electrons. Now this concept, penetration of electrons, we are calling as what? Tunneling. Tunneling is nothing but there is a tunnel from one region to another region. The electrons will penetrate from this place to this place. For a smaller applied voltages, that is not greater than barrier potential. For a smaller applied voltage also, due to the tunneling phenomenon, the current flow will take place. If it is greater than 0.7 volts, now see, in a tunnel diode, two types of currents will be there. Now see, tunnel diode, if it is less than 0.7 up to less than 0.7 barrier potential, the tunneling current greater than 0.7 volts. If it is greater than barrier potential, diffusion current will take place. In the forward bias, normal diffusion current will take place. That's why the characteristics of this tunnel diode will be, my voice, still it is breaking. My voice is not clear. Still it is not clear. Check once again. Still break. Now check it now. Is it clear? Is it? It's clear. Okay. Now, while I am speaking, it is breaking. Now it is now. My voice breaking. If people are saying, some of they are saying it is not breaking. People are able to follow my class. Now okay. Okay, chat box is not completely visible to you, but it is. I'm able to see your messages. I'm going very today. Okay, if you are not able to follow, there is one more discussion session is discuss all those things because we cannot see this. I can like you once again. I'm not enabling the discussion mode. There is a separate class allocated for the discussion. Now at that time, okay. Is it clear? Now, I will. There is a tunnel. Now, what is the tunneling case? Now it is clear. Okay, it is badly breaking. Okay. Now also. Okay, clear. From the starting only, I am not went anything. This is the starting slide of your tunnel diode. Yes, here I am having the LAN connection is very clear. I think still I connected my headset also. Still it is breaking. How many people are able to? Only one or two students that I think. Okay, audible, clear. Now those who are not able to follow, and now, okay, I will go very slowly. Now even though it is lagging means once check your network connection. Now at my point it is very clear. Now once again I am revising the tunneling concept. Now what is this tunneling is? Now in the normal case, in the normal diodes, what is going to happen? According to the normal mechanism, now only the tunneling, only the first point what I told in the tunnel diode is the width of the depletion region. That means, okay, I will come back to the previous slide also because some of you people, they said they're starting from the tunnel diode. I hope today it is 5:10. Only we are having 10 more minutes. Okay, the other name of tunnel diode is Isaki diode. And now the main difference between the tunnel diode and the PN junction diode is the impurity concentration is very, very high. That is a 1 part in case of 10 power 3 atoms. That is nothing but your tunnel diode impurity concentration. Now for PN junction diode, it is 1 part in 10 power 8. Very, very less impurity concentration for the PN diode. Okay. Now the width of the depletion region is very small. That means in case of, because the width of the depletion region is mainly depending on the impurity concentration. How it is? Now say this is the, I will remove all the things. Now see. Now this is nothing but your barrier potential VB. The barrier potential is equal to given by this is expression. The width of the depletion region that is inversely proportional to square root of your doping concentration. If more doping concentration is there, the width of the depletion region is very, very less. If very low doping is there, the width of the depletion region is high. Now take a simple PN junction diode. I am a simple PN junction diode. I am assuming this is the width of the depletion region. Now for the tunnel diode, if I am taking as a tunnel diode, due to the heavy concentration of doping, this is almost very thin layer. Now that is what. So width of the depletion, width of the junction, you may call it region. The barrier varies inversely as the square root of impurity concentration. Now, in the tunnel diodes, by increasing impurity concentration, Na is nothing but impurity concentration, the width can be reduced to 5 micro to 0.001 micro. That is very, very narrow. This is the width of the junction in case of your tunnel diode. Now, what is the basic classical mechanics? In case of classical mechanism, uh, basically whenever the applied voltage is greater than the barrier potential, then there is a charge carriers, they will diffuse from the one side to the other side. That is for the normal classical mechanics. But in how many people are not able to listen my voice? Just majority people try to put your message in the chat box. Okay. Now it is clear. It's clear. It is clear for some time, but breaking in middle. Okay. In the starting of my class only, I told. Now, if you are not able to follow due to the lag or due to some any technical glitch, now at the end of the class, I will share the presentation to your mail IDs immediately. Your CRs they will share to you. Now, so that first go through the presentation, then that class will be clear on the day itself. Okay. Right. Okay. The main thing is in the tunnel diode, in the normal PN junction diode, the diffusion of charge carriers will take place. That means current will flow whenever you are applying the forward voltage greater than the barrier potential. That means if it is more than 0.7 volts, then only the current will flow in the PN junction diode. Is it clear? Now, in case of tunnel diode, that is not the concept. What is the concept? Even though the applied voltage is not more than the barrier potential, still the current is flowing through the tunnel diode. That is due to the tunneling mechanism. Now, what is the tunneling mechanism? Now, even for smaller positive voltages, that means for a zero point 0.1 volt also, some electrons, now due to the thin depletion layer, these electrons, they are tunneling into the other side. That means from the N region to the P region, electrons will tunnel to the other side. When the electron is tunneling from one side to another side, that current is we are calling as a tunnel current. Now, if it is less than the barrier potential, the current is due to the tunneling of charge carriers. Greater than barrier potential, that current is due to your diffusion of charge carrier. Now, that's why this tunnel diode is little bit different compared to the normal PN junction diode. Once again, I am uh, 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 that means once again recapturing this. Normal PN junction diode, the diffusion of charge carriers will take place if you are applying more than barrier potential. But in case of your tunnel diode, now if it is less than barrier potential also, there is a current flow. That current is due to your tunneling of your charge carriers. Now, why the tunneling will takes place? Because there is a small depletion layer. Now, due to the thin depletion layer, the electrons they can penetrate from one region to another region. That concept we are calling as a tunneling mechanism. Right. Now, what is a tunneling mechanism? Classically, the carrier must have energy at least equal to potential barrier height to cross the junction. Okay, that means if it is having the minimum barrier potential height, the energy of minimum barrier potential, then the electron can diffuse from the one region to another region. But according to quantum mechanics, there is finite probability that it can penetrate through the barrier for a thinner width. That means if the width of the depletion region is small, then some electrons, they can penetrate through the barrier. Now this phenomenon is called the tunneling phenomenon, and hence the diode we are calling as Isaki diode. Isaki is nothing but Leo Isaki is the scientist name who proposed the tunnel diode. Okay. Now this is the VI characteristics of your tunnel diode. Now what is happening? Now this, see the voltage here. Now this voltage is nothing but generally this is my barrier voltage. Now in case of PN junction diode, now how it is looks like? Now up to the barrier potential there is no current flow. Whenever it is greater than 0.7 volts, this is for the normal PN junction diode case. Now see for the tunnel diode. In the tunnel diode, in the terminology, just remember IP is nothing but your peak current. The maximum current we are getting, this you are calling as the peak current. Now IV is nothing but your, this is the valley current. VP is nothing but with respect to this is the peak voltage. VV is nothing but your valley voltage. Just remember these four terminologies. And VF is nothing but peak forward voltage. Okay. Now this is the reverse characteristics of your tunnel diode. The forward characteristics of your tunnel diode. I will explain you this with respect to your band diagrams. The first one. Now this is a symbol for your tunnel diode. Already told you. And this is the equivalent circuit. The resistor in series with your inductor and in parallel with the resistance. Now this is the equivalent circuit of your tunnel diode. Now see the band diagram. And this is a simple energy band diagram in the thermal equilibrium in which both and NP regions are degenerately doped. That means degenerately doped. Now this is I am taking the N side and this is your P material. In the N material, now see this is your conduction band and valency band. In the P type, this is your valency band, this is a conduction band. You may get one doubt. Sir, Fermi level is middle of between these two now, but due to the heavy concentration, that means heavy doping concentration, now the shape of this band diagram also is going to vary. Now, just see this band diagram. If this band diagram is clear, the tunnel diode is clear. In the N-type material, now Fermi level is, this is a Fermi level between the P and N-type. This is the conduction band of your N-type material. This is the valency band of your N-type material. P-type material, this is the conduction band of P-type material. This is the valency band of your P-type material. Now, what is the normal diffusion process? Diffusion of charge carriers from the conduction band to the conduction band will take place. When it will take place, if it is more than the barrier potential, the width of the barrier potential will reduce, the height of the barrier potential will reduce, so that it will come in this fashion. These electrons, they can easily cross the junction. This is for the normal case. Now in the tunnel diode, we will see the operation. This is a basic band diagram at the thermal equilibrium. At the thermal equilibrium, N-type material will be looks like this, P-type will be like this. If you combine P and N, the junctions is going to be, the band diagram is looks like this. The Fermi level is, this is the Fermi level is above the conduction band, it is below the valency band for your P-type material. Okay, we'll have for this some 4 to 5 scenarios. What is the first scenario? At the zero bias. I am not applying any bias to the tunnel diode. At the zero bias, this point is nothing but at the zero bias. Okay, now this is the Fermi level. The dotted line is nothing but your Fermi level. Now, what is happening? A simplified energy band diagram for IV tunnel diode at zero bias. There is zero current on the IV diagram. There is no current. At the zero, it is all energy states are filled below EF on the both sides. Now, see this side. Now, this is nothing but your EF. EF is nothing but your Fermi level. At the Fermi level, below the Fermi level in the conduction band, all the electrons are filled in the N type. This is N type. And in the P type, below the Fermi level, this is your valency band. This valency band is filled with your holes. See, below the Fermi level, N side completely filled with electrons, P side completely filled with your holes. Okay. Now this is at the zero bias case. Now we'll go for apply some little bit forward voltage. Now what is going to happen? Now a small forward voltage I am applying. I am not applying the more than barrier potential. Just applied only 0.1 volt. Now for the smaller forward bias voltage, what is going to happen is, now here, what are there in this band? Electrons are there. In the valency band, what are there? Holes are there here. Okay. Now, due to this thin depletion layer, these electrons and these holes, and this is the C here. This side holes are there. This side electrons are there. These electrons, they will penetrate from this area to this area. Up to what extent it can come? Now, up to this extent, now these electrons, they will penetrate into the P region. The current due to this penetration of these electrons, that you are calling as this nothing but your, this is the current due to your tunneling current. What was happen here? These electrons was tunneled from N region to, they are not diffused. When the diffusion will occur? More than the barrier potential. But still I am not applied the barrier potential. How much I applied? Very small forward voltage I applied. For the small forward voltage, what was happened? Electrons in the conduction band of the N region are directly opposite to the empty states in the valency band of P region. These are the empty states of your valency band of P region. So a finite probability that some electrons tunnel directly into the empty states, resulting in forward bias tunneling current. Now there are empty states are there in the P state. Now depletion region is very thin. Some electrons, they tunneled through this region and they occupied the empty states. Now the electrons are moved tunneled from N region to P region. The current due to this you are calling as a tunneling current. Now this is a case for you are applying small forward voltage only. Okay, go for the next scenario. At a when the maximum tunneling current will occur, because this is the completely filled conduction band of your N side. Now this is the completely available free space of your P type. Previously only this is the case, this portion only available to us. But now if you are increasing the positive voltage, that is not greater than the barrier potential, now maximum number of electrons will tunnel to the P side. Now the maximum number of electrons in the N region, they are opposite to the maximum number of empty states in the P region. Hence the tunnel current is maximum. Here the tunneling current will be maximum. Now, next what is going to happen? Still you are increasing the more positive voltage. Now I am assuming this is for 0.3 volts. The previous diagram is for 0.1. This is for 0.3. Next, if you apply 0.5 volts, now what is going to happen? Now this is going upside. Now the conduction band is going upside. This is going downside. Once again, the free states will be only, this is a small portion. Once again, the current will reduce. The current will be reduced. Okay. Now, still if you are increasing the more and more at the higher forward voltage, that means that is greater than 0.7 volts. Now this is completely going to the upside. The conduction band is the moving. The band is moving very higher and this valency band is completely coming to the down. Now these electrons, they can diffuse to the P region. Now that's why at this point onwards, this characteristics curve looks like your PN junction diode. Whenever it is greater than 0.7 volts, this is looking like your characteristics of PN junction diode, forward bias characteristics of PN junction diode. Now in this case, at the higher forward voltage, no electron on the N side are directly opposite to the empty states of the P side. Therefore, tunneling current is zero. There is no tunneling of charge carriers. That means these electrons, they are not entering into this area. That's why the total current at this point at the maximum higher forward voltage, that is due to the diffusion of charge carriers. This current we are calling as a forward bias current. Okay. Now at the reverse bias, what is going to happen? In the reverse bias, the reverse phenomenon. At the forward bias, electrons from the N side, they are penetrating into this side. But in the reverse bias, these holes, they are tunneling into the N region. Now that is due to the reverse bias voltage. Now electrons in the valency band of the P side are directly opposite to the empty states in the conduction band on the N side. Electrons directly tunnel from the P region to N region. The reverse bias current is increases monotonically with the reverse bias voltage. That's why it is linearly increasing with the reverse voltages. Now this is the VI characteristics of your tunnel diode. It has a nearly 5 different stages at the zero bias. At a smaller forward voltage, at the maximum, that means more, that means less than barrier potential, but greater than the smaller potential. Third one is at the higher potential voltage, higher positive voltage. And the fourth case is at the reverse bias voltage. So this is the VI characteristics of your tunnel light. What I said till now, that I kept in the statement fashion. Just read the statements, then you will get the full clarity. Now, what are the typical values of your tunnel diode? The peak voltage is 50 millivolts. The valley voltage is 350 millivolts. The VF forward voltage, the maximum voltage is 0.5 volts. IP by IV is 8, it's a factor. And these are the typical values. When you are using the tunnel diode in the practical application, these are the typical values you are going to use. And what are the applications of this tunnel diode? They are going to use a high frequency oscillator. It is a very fast switching device. Switching time is in the nanoseconds of time. Since tunneling is a quantum mechanical phenomenon, there is no time lag between application of the voltage as well as the current variation. Okay, this is with respect to your tunnel diode concept. Okay, I will share the today's presentation to your CR's mail ID and go through that, and everything will be clear. Okay, just within 2 minutes, I will show you the virtual simulation of this tunnel diode. 5:30 we'll start the today's class, today's quiz session. Now take a tunnel diode. This is your tunnel diode, IV curve. Now see the voltage with respect to your curve, how it is going to happen. Now I'm resetting the status. I'm slowing the simulation speed and the current also. Now see what is happened. Now see current is first forward voltage is more. Now it comes down. It slowly it is tunnel current is reducing and it is P injection diffusion current. And the same in case of reverse bias also the same scenario. In the reverse bias voltages it comes. Now you can observe it is the input voltage I am applying with respect to this input voltage. Now how the current is changing. Now see the current flow here. When the maximum current is flowing, then you can visualize. Now this is the current flow in case of your tunnel light. This I will share to your CR's group. These applets you can simulate with the help of JVMs. If only Java virtual machine is there in your laptop, then you can visualize and you can apply your own values by changing the input voltage. By changing the parameters, you can visualize all the complete parameters. But these are the basic simple circuits so that it is very easy to understand. But if you are going for the advanced classes, that is a PN junction diode and JFETs and the advanced cases, this will help you very lot while understanding the complete concepts. Okay, now we will start the quiz. And now the time is 5:28. Now we are giving you the 15 minutes time. Take the quiz. Madam, start the quiz, ma'am. Now with this, today I am stopping. In the next class, we will continue the remaining two more breakdown diodes. One is photodiode, second one is light emitting diode, and then followed by the rectifiers. Okay, with this, today I am stopping. Now we will complete our quiz part. Now all of you take the quiz. Already quiz was started by ma'am. Yeah, quiz already started. All of you take the quiz.